Okay. All right. So let's keep going with probabilistically checkable proofs. Let me briefly remind you what we're trying to prove. We're halfway through, or we should be, because it's only 2 classes allotted for it. So, and this is a lecture that's putting together a lot of the tools we built, especially involving random walks and spectral graph theory and stuff like that. And so we're trying to prove a tremendous theorem. It takes a while to get there. Which is okay, so probabilistically checkable proof. So the idea is that, okay, a problem, is in PCP RQ. R stands for number of random bits the verifier uses, and Q is the number of bits in the proof that the verifier looks at. Okay, so it's going to be like the MP setup where you have the input and the proof that the input's, what you're looking for. It has a Hamiltonian path or something. But we're interested in trying to develop verifiers that only have to look at a small number of bits in the proof and then be able to say with confidence, it's a fake. Okay. So in particular, your language is in PCP-RQ. If you have a verifier that uses R random bits and looks at Q bits of the proof, and if X is in a language, like X has a Hamiltonian path, it should always say yes. If it's not in the language, just by looking at a few bits in the proof, it should find a mistake. Okay, so then the joke that Corbett alluded to is that, if we can only set up our homeworks this way, right, then you can just look at a few bits of a homework, figure out the students have no idea what they're doing, and then you'll be done with it. And this is like kind of true. I mean, if you grade a lot of homework, you can kind of recognize pretty quickly. Okay, so the PCP theorem, after we did a big vote, says that NP is equal to basically a constant number of query bits. Okay, so any problem in NP, somehow you can adjust the proof and you can do some reductions and get it into a state where you only have to look at a constant number of queries in the proof to be able to say with some confidence, this is wrong, if it's wrong. Okay, and that leads to a number of results, including, when we toss 3 coins for 3 sat, we toss coins for 3 sat, you get 7/8 for free. And in fact, you can't do better. Okay, that takes more work, but it starts with the PCP theorem. Okay, and so one direction is kind of easy. Now, what we were proving, we focused on these constraint satisfaction problems, really binary constraint satisfaction problems. So these are problems that have 2 variables as input, and those variables can be one of some finite number of options, like graph coloring, it's one of 10 colors or something. 2 sat will be true or false. And each constraint just accepts some possible assignments and rejects some others. Okay, so it just generalizes graph coloring, sat, things like this. And what we were trying to prove is that the following problem is NP hard for CSP for even a finite alphabet size and a finite airiness, like binary, in fact, is what we're doing. And it's NP hard to tell if, I give you a constraint satisfaction problem, so there's a bunch of constraints and some variables. To even figure out if half of them can be satisfied is NP hard. Okay, so it's NP hard. So, normally we focus on completely satisfying or you can't. But this says, look, even up to 50%, you can't do better than. Okay, so there's this huge gap there. This is also kind of an inapproximability result, right? It's saying you can't get better than a factor 2 approximation for CSPs. Okay, even with finite alphabet size. Okay, and then we did this kind of back and forth last time, to show that these two things are equivalent. In one direction, like you want to take the problem on the right, the CSP problem, and come up with a PCP verifier. And that verifier is very simple. Just sample a random clause. So if this thing is not satisfiable, then at least half of them should be wrong. So if you just pick one random clause and check to see if they satisfy it, you'll find a mistake with probability 1/2. Right? In the opposite direction, if you have a language that only needs to make a constant number of queries and uses log n kind of random bits, you can make a clause for every possible random bit string. Okay, and then you build a constraint based on the bits it's querying. Okay, and so PCP says, look, if that thing is not in your language, then you should be rejecting it half the time. That's going to map exactly to half the clauses being wrong. Okay, so I'm going a little quickly because we did this more slowly last time. Okay, so what's our setup? we want to show that it's hard to do a half approximation for constraint satisfaction, essentially, or two approximation. Initially, it's empty hard to distinguish between 0 and a single error. So 1 over m or something if there's m constraints. And so the first thing is kind of how do you ramp this up to 1/2 error? So somehow you want to do some kind of reductions so that there's really no big difference between having 1 error or half of them error. Okay, so at some level, we're going to try to add redundancy. So the first kind of natural idea is to do something kind of like powering. Like, okay, if I start with my constraint satisfaction problem, I have 1,000 constraints. Why don't I, for every possible combination of 5 of them, create a new constraint saying you have to satisfy all 5 of these, right? This way, your one mistake is going to show up in a lot of bundles, and it's going to kind of gradually increase the error. The only problem is you're going from 1,000 constraints to 1,000 to the 5 or something, right? So it's blowing up quickly, and you can't just like take your polynomial size thing and make it exponential and say, but the error is high, right? Because a polynomial time algorithm on your exponential size thing is only allowed to use exponential time on your original input. Okay, so there's some question of how do we add robustness in an economic way? We want to maintain the size. We don't want things to blow up. Okay, so it's a bit like error correcting codes. You're trying to come out somehow add redundancy in a very efficient way. Okay, so to that, and it's very helpful to focus on binary CSPs or graph CSPs. So that means every constraint just involves 2 variables, which means you can always visualize it as a graph, right? Where you think of a constraint as an edge. The only thing is that this graph, every vertex also gets annotated with whatever like letter you assign to it or color. Okay, so then let us remind us what our approach was going to be. So at some level, we're gonna do a cycle of 3 steps, right? And somehow it's going to be a net win. The first step is to make the graph an expander. I'll remind you in a moment, but this actually was not so complicated. And then the next step is what we're going to pick up the discussion. Is we're going to try to take advantage of the graph being an expander to do a more efficient powering step. Okay, based on random walks. And I alluded this a little bit last time, but the alphabet size is going to blow up in order to keep things like a graph. And that's going to be addressed in the last step, which will require black boxing a little bit, but I did expand out the slides for this. So you can at least see some more connections. Okay. All right. So just to remind us, I want to take G and make it a constant degree expander, right? So that means I want the graph to have very small degrees, so it looks like a sparse graph, but somehow it should act as if it was super well connected. A random walk should go anywhere really fast. And we just did 2 tricks. One was to take each vertex and split it up so that the degree gets small. But one important thing is to make sure that you have an expander in between so that things are pretty well connected. Okay, so this constant degree expander ensures that you're not adding too many edges in between. It's not that much worse than just adding a cycle, but it's going to be kind of better connected as a cycle. So you're discouraged from doing things like setting some of your auxiliary variables to one thing and the others to another, and stuff like this. Okay, so yeah, somehow once you get very comfortable with the existence of expanders, you start saying, oh, it can do this magical thing for you. It can do that magical thing for you. Okay, and then how do you make it an expander? Well, this is kind of silly, but we just take our graph with bad expansion, but good degree, and then throw any graph you want with good expansion and constant degree on top, right? So let's say our original graph, has like degree 5 or something, and then I add a constant degree expander, it has another degree 5. So I've only doubled the number of edges. Okay, so I've made the expansion good because the constant degree expander, and then I'm going to add trivial, always happy constraints to every edge, right? So all those, yeah.
Would this be an issue if you're trying to add an edge between two nodes that already exists?
You're allowed to have parallel edges. Yeah, I guess I don't draw them, but you can have parallel edges. So we can add some trivial, the expander we throw on top, we don't really want it to affect the logic of the problem. So we'll just give them trivial constraints. They're always satisfied. So that's going to drive unsat down. Our goal is to drive unsat up, right? We want the error to be high, but how much is it going to go down? Like, let's say you had degree 5 originally and you add another degree 5 on top. So you've just doubled the number of edges, right? And number of edges is number of constraints. So unsat is some numerator divided by some denominator. The numerator stays the same, right? Your mistakes are still mistakes, and you've doubled the denominator. So unsat will go, down by a factor of 2, but the point is that's under control. Okay. Powering, we're going to kind of be able to increase it sort of arbitrarily because it's going to be parameterized. Okay, so that's sort of just a pre-processing step. And now we'll get to the powering, which is where a lot of the action happens. All right, good. Okay, so we started discussing this last time. At some level, we want to get around the fact that just taking arbitrary, combinations of t constraints will blow up the size, although it kind of will mix things well. We want to not blow up the size, but still mix things well. So now that the graph is an expander, we're going to try taking, t-step walks and adding constraints for each of those walks. Okay, so let's say like t is, I guess, 3 in that picture or something. But at some level, every 3-step walk is going to turn into a constraint. Okay, and now one weird thing about this is that, okay, so now I'm saying, okay, I have these 3 edges, and they're only satisfied if kind of all of them are satisfied. Now, if you think of those 3 edges, there's sort of like an edge in the middle where the vertices are in the middle and have nothing to do with the endpoints, right? But I really want to pull out like a graph CSP where I'm only looking at the endpoints. Okay, so somehow I want to figure out how to get a substitute for those missing labels in the middle because I'm only going to look at the endpoints. So to do that, what we're going to do is we're going to blow up the alphabet size as well. Okay, so like in this picture, I start at V and I say, okay, how many vertices are within 3 edges? It's 3 hops away, right? Then all of my constraints are going to kind of be contained in this neighborhood. I mean, all my powered constraints. And I'm going to increase my alphabet size from just A to A raised to however many vertices in this neighborhood. It's a regular graph, so it goes up by some fixed amount. Okay, so in other words, instead of I can't count how many arrows would there be here. It's like 4 to the third or something. There's 64. Come on, you kids are clever.
He said 39.
Seriously? 1 plus d to the t. D is 3. 4 to the 3. 64. Okay, let's say there's 64 nodes here. Okay, so instead of just assigning 1 letter to V, I'm going to assign 64 letters to V. Okay, so the alphabet size goes to A to the 64, but I'm going to interpret that as V kind of assigning 1 color to everybody in its neighborhood, including itself. Okay, so I'm going to blow up the alphabet size, but we're going to interpret that as kind of it labeling its neighborhood. Okay, and so what's that going to do? Now, when I define, a constraint, really between 2 endpoints, but it's modeling some, say, 3-step walk. Okay, but I only want to look at the endpoints to see if it satisfies. It should be a constraint between the 2 endpoints. But I can look at V0, and V0 has a letter for everybody in its neighborhood, including everybody on that constraint. Okay, so V0 has some opinion of V1, V2, V3 up to VT. And also VT, the graph is undirected, so it's going in both directions. VT has an opinion, again, of a letter for everyone along the walk. Okay, so finally, when I want to define, really, I want to turn this walk into a single constraint between V0 and VT, the 2 endpoints. I think this is sort of natural. I want to make sure that V0's labels satisfy all the constraints along the walk. V0 has a label for every vertex along the walk, and it needs to satisfy every constraint. Same with VT. VT should make everyone happy, right? That just makes sense when we're taking a conjunction. And the last thing to make sure we don't cheat is we're going to also require, I guess it's hard to see the lime green, but V0 and VT should agree on all of these letters. Okay, and then that will give me a constraint that only has to look at these jumbo letterings on the 2 endpoints. Bye, Josh. Okay, so I only have to look at these jumbo letterings at the 2 endpoints, and I kind of infer along the line, and I make sure they agree. Okay, so that's okay. The alphabet size blows up. Otherwise, and it's kind of messy, but I think it's kind of logical. Okay, what's on this slide? Oh, this is some picture. Uh, well, okay, you get the idea. Okay, so our claim is going to be that when I raise it to this tth power, the unsat is going to go up by basically a square root t factor. Okay, I want to point out t is going to be a constant. So if unsat is already at least 1 over t, then I'm basically happy I've proven unsat is at least a constant. I don't think we'll get all the way to 1/2 in these slides, so just getting to a constant is fine. So if unsat is already at least 1 over t, then I'm happy. So in the interesting case, we're really increasing things by a square root t factor. Okay. All right. Good. Um, good. Let's see if anything's written. Okay. That's what I said. Okay. All right. Uh, yeah. Okay. The proof is going to be messy. For some reason, I thought it would be nice to think about how to even set up this kind of proof, how to frame it. Also, kind of make sure we're on the same page. So if you want to prove this, like what might you say? Suppose you had this. What would this be? Okay. Okay, so what we're going to do is we're going to say, okay, suppose you had some assignment to the powered graph. Okay, so I'm going to use pi bar. That means you're assigning a jumbo of letters to every vertex in the powered graph. And what we're going to do that, we're going to try to extract an assignment to the original graph. Okay, and to prove our claim, I want to show that the lifted or kind of extracted assignment, the number of mistakes it makes is at most something times the number of mistakes made, proportionately as a percentage, as before. What might go in the box? All right, 1 over root t. Okay, so if I can show yeah, okay, so if I can show that the error in the lifted one is substantially smaller, so it's kind of the contrapositive, basically. Okay, but we're going to start with a labeling in the blown up problem and then try to lift the labeling in the original. Okay. Um, all right, so let's say you have some optimal, labeling in a blown up problem and achieves unsat g to t. Now that's assigning to every vertex, a ton of letters, right? We want to lift that and somehow get 1 letter per vertex. Okay. Any ideas?
Randomly choose based off all segments.
Randomly choose based on. Okay, so if I'm trying to figure out V, a good letter to choose V, what might I do procedurally?
Check the box from B to 3.
Okay, so I can check all these guys, right? So I check all these guys and then what?
Store.
So all of these guys have their own jumble of letters. Okay, and then
Look at these summary of each one.
so everyone in V's neighborhood has a label for V because it's symmetric, right? So kind of, so in the lifted problem, V is a kind of appearing as a label inside all of these other vertices. And I want to pull out kind of one good one, yeah.
You choose one that's in all of them.
Well, they might disagree, right? They're not required because we're just doing it's not an all or nothing exact thing, right? So it's possible that the optimum solution, wants to mix these up. Some of these vertices have some opinion, maybe all of those guys think of the same letter, but then these guys have a different assignment for V.
Choose the most popular.
Okay, a reasonable thing is maybe to choose the most popular one, some kind of majority vote. Okay, so that's what we're going to try to do. So we're looking at a neighborhood in a certain way, and then figure out, someone will take a popular vote of what everyone else thinks of V. Okay, we're going to be kind of calibrate the vote as follows. So, all right, starting from here, suppose you took a t over 2 step lazy random walk. Okay, so that might go to here or something. Okay. So these are also vertices where like V kind of appears in the middle of these t-step random walks in general. Okay. So yeah, something like this. And so I take a random walk and I look here and I look back and say, what does this kind of destination think of V? It's some random letter. Okay. And out of this experiment, we can just pick the most popular one. Okay, we'll just define it to be the most likely one to appear in this experiment. So slightly different than just looking at all the vertices in the neighborhood. Yeah.
V thinks of any other vertex equals what that vertex thinks about me.
Yeah, so we're going to assign to V something based on what other people think of V.
But I'm saying is the label that V gives to that other vertex the same as the label that that other.
Not at all. They don't have to be symmetric. We're not assuming that like pi bar is nice. We're just assuming pi bar is optimal, and maybe there's some reason, based on how the graph is sorted, that this one might want to assign some one particular letter to V because it's participating in these constraints. That other vertex wants to assign a different letter to V because it's participating in different constraints. Because once we start splitting these up and stuff, right? It's not required to be the same. We added some stuff to motivate it to be the same, but it doesn't have to. Yeah.
Constraint C. Like they all agree.
Yeah. So basically, that just means that because we're not doing completely satisfying or not. So pi bar doesn't satisfy all the constraints. It will want to get that constraint, but it might not. Yeah. Yeah. So all these kind of approximation preserving, more quantitative reductions get a little trickier. By a little, I mean a lot. Okay. Now, one thing nice is that if I pick pi v to be the most likely letter, now suppose I take a random walk. What are the odds that it's equal to pi v? I mean, suppose, or at some level, like what are the odds that, this random letter is equal to the one we choose?
The wall distribution.
Well, let's say that there's 10 letters in the alphabet.
It's greater than what's
It's at least 1 over 10, right? So we have a constant of it's the mode of the distribution or whatever, which is the only time I've ever heard of the mode being useful. Okay? So okay, pi v is sort of this random experiment. You look at a random neighbor and you see what it thinks of itself. And that's some kind of popular vote. Okay. And it's not obviously it's going to get a lot wrong, but it is always going to get at least a constant fraction right because the alphabet is finite in size. Okay, so all that matters is constant. Yeah.
holding this.
Yeah. So the experiment is I start at V. I take a t over 2 step lazy random walk. So each step I stay or I go. And then I land somewhere else. And that's somewhere else. Remember, this has a big mumbo jumbo of letters. And in particular, the mumbo jumbo here has some assignment for V. Okay, so that's just a random experiment.
What do you mean by most likely? Is this over one trial?
No, most likely, if I did this this will give you some distribution of random letters.
Oh, okay.
and then one of them is the most likely one, and that's always at least 1 over the alphabet size. Okay. And you don't have to actually do this in any algorithm, right? This is just a reduction, so you have to show it exists. So we don't have to worry about implementing this thing and how fast it converges or something like this. Okay, although I think it wouldn't be bad because 1 over size of A is big. Okay, good. All right, so that's how we're going to lift this kind of multi-assignment to a single assignment. Okay. Okay, so what are some kind of high level ideas, right? Suppose your single assignment fails an edge in your original graph. Okay. Now, if I take a kind of lazy random walk from the two endpoints of that edge, right? With constant probability, where I land is going to have the same label as the one I pulled out, right? So I start from U, I walk around for t over 2 steps, and I go somewhere. And same with V, I walk for t over 2, I go somewhere, right? And those two vertices have a constant chance of giving the same label that I actually pulled out, right? 1 over size of A squared or something, because there's two of them. Huh?
Just hope.
U and V are the endpoints of this edge you failed. Okay. And that means that this random walk and the corresponding constraint, t step constraint or t plus 1 step constraint, or t step, is going to be failed in the powered graph, right? So if you took a random, so in your regular graph, you failed this edge. That means if you took a random walk, you have a good chance of getting to endpoints that failed the whole kind of walking combined constraint. Okay, so if you're failing a constrained original graph, you're hoping that a lot of these lifted, a lot of the bundles that have this edge close to the middle are also going to be failed. Yeah.
So the random walk, do you mean like a random walk total length t over 2 in the power graph, like including UV?
No, it's a t over 2 steps in the original graph, but it's also lazy, so it's like t over 4 on average. The t over 4 real ones on average. Okay. So, but if you concatenate those random walks through that particular edge you failed, you're getting a bundle in the bundle graph. All right, so good. So these things will fail with some constant probability. So in the lifted graph, yeah. Okay, so you're hoping that you fail a lot of bundles because you're pulling out some kind of majority opinion, right? If you pull out like a majority opinion and the majority opinion's wrong, then at some level the majority is kind of wrong. Okay, you have to kind of make that precise quantitatively, but that's the idea. Okay, so good. So a constant fraction of walks is E, roughly in the middle, are going to fail. We're not really saying anything about the constraints where E is off at the edges, just the ones close to the middle. Okay, good. Nothing down here. So that's the high level idea. And the question is, okay, now I have to do some math to make this precise. Okay, so we're gonna need two lemmas. We'll see. Okay, most of it's prepared ahead of time because I was afraid I was gonna make a mistake. You'll see. Okay, so so this is actually a really subtle but important point. So I'm gonna focus on at some level only indices that are very close to t over 2. Okay, because you have some kind of t-step random walk or something in each constraint. I'm only going to kind of focus on indices that are very close to t, within roughly square root t. That's roughly kind of a standard deviation, and we'll see why that's useful. Okay, and now suppose you take a lazy random walk starting from V. Okay, so so the claim is that for all the indices that are close to t over 2, um, that because our experiment was exactly t over 2, right? You took exactly t over 2 lazy random steps and then you looked. Okay, this is saying for any index I that's very close to t within square root t, which is small compared to t, okay, you're also going to get somewhat similar probability, at least a constant. Okay, so we're kind of trying to make things a little bit more robust because originally I pulled out this assignment based on exactly a t over 2-step random walk. Now I kind of want to get a similar conclusion over random walks as close to t steps, but not necessarily exactly t. Okay. Any guess as to the intuition? So a really important fact is that we're talking about lazy random walks here. Does that help? So you're taking t over 2-ish lazy random steps. Okay, so square root t represents one standard deviation, right? So at some level, like, okay, if I tossed, uh, uh, yeah, if I tossed a million coin tosses, and we said, okay, how many came up heads? Or if I tossed a million plus square root of a million coin tosses and asked how many came up heads, how do the distributions look? Sorry? So square root of a million will represent kind of one standard deviation, which is some kind of area where all the probabilities are pretty similar. Okay. You have a decent chance of always being within a standard deviation. So square root of what? So okay, if I flip a million coins, you're expecting 500,000 of them to be heads or something, right? And it's going to kind of a lot. You'll get a lot between 500,000 and 500,000 plus square root of a million, which is 1,000, I guess. Uh, and so if I toss, 1,000,000, 1,000 coins instead, I'm still basically roughly in the interval of 500,000 plus like 100,000 plus or minus 100,000. Okay, so this is so small that the number of heads you get isn't that different. The odds of flipping a million coins to get 500,000 heads is very similar to the odds of flipping uh, a million and 1,000 coins and getting 500,000 heads. Same with 500,001, 500,002, 500,003. Okay, so those overall distributions aren't that different. Okay, how does that relate to lazy random walks? What would the heads correspond to? The heads will correspond to taking real steps. So out of t over 2 lazy steps, half of them are fake, half of them are real on average. How many real steps did you take? And what we're going to try to argue is that for any I that's close to t over 2, the number of real steps is almost the exact same distribution. Yeah, undirected. Everything's undirected. I just often draw directions because we're like to trace the walk. Yeah, but the CSPs are always undirected. Yeah, yeah. Okay, the underlying graph is undirected, and sometimes as walks, I draw them as arrows so we can kind of imagine walking. Okay, so I guess that there's more details in the notes, but that's okay. Let's let ji be that random variable saying how many real steps are you going to take in an I-step lazy random walk. Okay, and so it's the number of heads in I coin tosses, and then if you do the calculations for all I and I, okay, ji is going to be distributed really similarly. Okay, that's what this picture, I guess, is supposed to represent, right? They're almost overlapping. Okay. So so what does that mean? If you condition on the number of real steps you take, right? Once you condition on number of real steps you take, then everything is independent of I. You don't care about how many fake lazy steps you're taking once you know how many real steps you're taking, right? So once you condition on the number of real steps out of I you're taking, you don't need any information from I anymore. Okay, so if I have two different values of I, but the j's are distributed almost identically. Then I can just kind of set up the conditional stuff, and the only difference is the difference in distribution of j's, which is very small. Okay, so basically everything for every t over 2 plus 1, t over 2 plus 3, t over 2 up to plus square root t or so. Okay, you're basically going to get the exact same distribution of number of real steps, and that actually determines where you end up. Okay, so that's why the lettering comes out similar. Okay. Okay, good. So that's one lemma that I won't do all the. I'm not going to do as many details as I often don't do many details, but we're going to do even less today because there's just so much going on. Okay, they're either in the notes or left as exercises in the notes because they're doable. Okay, they exercise in the sense. All right, so here's a second lemma, which again we also won't do in detail, but should be really familiar to you guys. So you guys could also do this lemma yourselves. It would take some time, but okay. So suppose I took a lazy random walk. Uh, so suppose out of the graph I have some set f of bad edges, and suppose I took a lazy random walk where the first I start uh, was a random edge, maybe in some direction, kind of either direction, uniformly at random, and then I keep walking from there. Okay, what is the probability that the ith edge is an f? Okay, an upper bound. So you expect when I is small, it might be a little higher because the very first edge is inside, and maybe in the worst case you're because this is over all possible ways of distributing f so that it occupies say half the graph or something, right? And maybe I've set up the graph so that if you sample an f, you're kind of stuck on the inside of a big set of f, right? But you're hoping that over time, as you walk away, you have a better chance of getting out. And over time, once you get to a lot of steps, you're hoping it's kind of, oh, you could be anywhere uniformly at random. So it should kind of approach mu over time. Okay. So this appears to be the case. So you can show that this will be at most mu plus 1 minus gamma to the I. So there's something decaying based on the spectral gap. Okay, this looks almost exactly like what we did a couple weeks ago in that before we had a bad set of vertices we were trying to escape. This is sort of a bad set of edges that you're kind of going in and out of. Okay, but you very much can prove this in the exact style as before. I think the setup is the exact same, and only a couple of calculations will change because you're proving something slightly different. Okay, so you break it down, bad edges, good edges, the indicator vector, stuff like this. You can do the those matrices that drop all the mass or something. Okay, so it's broken down as an exercise in the notes. I think I'm going to focus more on how it's useful. Okay, so we're going to use f to represent the edges we fail. Okay, so good. So we're going to let f be the set of edges we fail. Then mu, this kind of fraction, will be the unsat. Okay, and I'm going to assume unsat is at most 1 over t. Otherwise, I'm kind of already happy and stuff, or I can just drop stuff. Okay, good. All right, so okay. Again, so what I want to show is that if I'm kind of making you want mistakes in your original graph to turn into many mistakes in the lifted graph. Okay, so now suppose I have a walk from a uniformly random t-step lazy random walk, and it starts at v0, it ends at some vt, and let's look at the ith edge along this walk. Okay, all right, so I'm going to have a random variable between 0 and 1, and I'm going to set it to be 1 if the endpoints agree. Okay, I mean, I'm consistent, which will happen with some constant probability. But pi fails this constraint. Okay, then that'll, I think, mean that v0 and vt also fails. Okay, good. So, right. So if I picked did a uniformly random walk, which is sort of like picking one constraint in the lifted graph uniformly at random. Okay, and I did this, and I get 1. Uh, if if I get a single mistake, then that's an error on GT, right? But this is sort of like picking a constraint uniformly at random and seeing if I make a mistake. So unset G to the T will be at least this. Okay, unset G to the T could be higher because there could be other mistakes and stuff like this, but that's at least one source of mistakes. So what's left is trying to analyze the probability that X is greater than 0. Okay, I realize it's a little bit of a whirlwind, but if at least the calculation sort of makes some sense in a moment, and you can at least see the connection ideas getting connected together, then there's plenty of time to think about it for the rest of your life. Okay. Okay. So I want to show this kind of probability of X greater than 0. I want to point out though that we are only looking at the indices close to the middle. Okay, so I'm only looking at the EIs close to the middle. That's one reason why unsat G to the T could be much bigger, because I'm not even worried about the constraints at the edges. Okay. All right. Good. So here's a lemma that's very cute actually. It doesn't have a name. It just like shows up in this paper. I hadn't seen it before. All right. Let's say you have some non-negative random variable x. Okay. And so normally from Jensen's inequality, you know that the expected value of x squared is at most the expected value of x squared. Okay. So you have some any convex function, right? And your random variable is kind of like going along this x-axis, right? And there's some expected value of the random variable, which attains some value, which it looks misleading because I drew it at the minimum. Okay, and then there's an expected value of the function, which is taking some kind of convex combination of things up above. Okay, so essentially convexity kind of boils down to the usual line above is above anything in the middle. Okay, so that's Jensen's inequality. But Jensen's inequality only gives you expected value of x squared is less than or equal to the expected value of x squared. Okay, and this is a much stronger because probably x greater than 0 could be small, right? So it's actually decreasing the right hand side. So stronger than Jensen's inequality. Okay, this is the only place I've seen it used though. But maybe if you keep your eyes open, you'll find one in your lifetime. Okay, I'm sure it's got to be out there. I don't know. I just really cute. Okay, so this one is not so bad to do. All right, so I start with expected value of x squared. Okay, what should we do next? Oh, is that what I want to do? I think I want the 2 on the outside. Yeah, I want the 2 on the outside.
Just the variance.
Sorry?
Difference is just the variance.
Difference is just is there easier proof? Uh, so I'm not sure if you see that.
It's a p greater than
Yeah, the p is the whole point. The right hand side, what's in yellow is what you get for free. Okay, so
Could you condition on x being greater than 0?
perfect. That's what we'll do. That's why we wanted the square on the outside. Okay. Oh man. Okay. Now what? If you didn't see it. All right. So now we're going to use Jensen's inequality on the conditional random variable. So you get that x squared thing again. Because the conditional x squared, so that's another random variable. Okay. Now what? Oh, there's something missing here. Sorry? Yeah, now you can pull one of those probability x greater than 0 on the inside. So somehow it's just some like cute trick proof where you just tweak Jensen's. You still use Jensen's, but you use it conditionally and you get this stronger bound. Okay. Why is that useful? Because now, I want to try to bound probably x greater than or equal to 0. It's the odds of making a mistake. That's unsat GT, right? And now I have this kind of term. Oh, Yes. Well, that one we know how to bound. But if you can bound this, then you're really in business. Okay, good. All right. I think I'm just like drunk when I make these slides. Okay. Uh, yeah. All right. Okay, so now we're going to start trying to look at the expected value of x and expected value of x squared and things like this, right? I mean, because probably x greater than 0 is sort of a brittle thing, but I think the nice thing about this ratio is it's quantitative, right? I'm looking at expected values of things, and that's maybe easier to analyze. Okay, so so right now W was sampled based on choose any random lazy walk. So to try to analyze this, we're going to sample a little differently. So for a fixed value of I think we're going to first sample an edge. We're going to sample a middle edge basically uniformly at random, and then we're going to grow it out. So we're going to take I lazy steps on one side and t minus I, or maybe t minus I minus one or something, lazy steps on the other side. Okay, so instead of picking any random one, you could pick something in the middle and then grow it outwards. You get the same thing. I think here it probably helps that everything is regular and things like this. Okay, so okay, now what is the probability that xi is equal to 1? Well, I guess it's going to first break into 3 terms. Anyone wants to guess any of them? Of course, I don't remember which is which. Okay, so you make a mistake if well, let's just see what's underneath. Okay, so one endpoint agrees with the label, another endpoint agrees with the label, and then what are the odds you make a mistake? So the endpoints need to agree with your lifted thing, right? And you have to make a mistake on EI itself in your single assignment thing, which is what we define what we define mu to be. So mu is our error in the input graph. Okay, and this is only going to go down a constant because the endpoints are going to agree because you took a popular vote. Okay, so constant fraction of time. Okay, so you get some big omega of mu. Okay, good. Um, fine. That means if I have square root t of these indices, it's going to multiply it to square root t times mu. All right, next claim is that expected value of x squared is less than or equal to big O square root t of mu. We'll just see how we did that. Okay. Okay, we're gonna have to work a little harder. Okay, so this is going to be some sum of xi squared, right? So we're going to have to handle all these cross terms. Okay, so the claim is a cross term. So the odds of making a mistake on the ith and jth edge for 2 indices in the middle is this thing. Okay, but then does it look familiar? So I want to guess where it comes from.
J minus I minus random walk.
Yeah, and so this is guessable.
Probability we started at.
Yeah, okay, so what are the odds you make a mistake on both, right? So first, the first edge, say EI, has to be there. And then, as suggested, you take a j minus I minus 1 random walk to get to EJ, and you make another mistake. Yeah. And so what does that look like? That looks a lot like, it starts to look more and more like this lemma. If you start a random walk in F, that's one of your mistakes, and you take a few steps, what are the odds that other step is also a mistake? Okay. So I think that's the whole proof. So the one outer mu is first xi is a mistake, and then the next term is you take a few more steps. What are the odds that one's a mistake too? And we have this upper bound. So let's see if it's written. Oh, this is going crazy. Okay, yeah, okay, that's exactly it. Okay, so y just says it's a mistake on I or something. So the first one is mu, and then conditional on that first step being a mistake, what are the odds that 10 steps later it's again a mistake? Well, it's that term. Okay. All right, good. So that's how you get this thingamajig. But it's basically mu squared. Uh, yeah. And remember, mu is at most 1 over t, so mu is very small. Okay, so I guess once we start trying to put these things together, all right, expected value of x squared is summing all I, expected value xi. Here, xi squared is equal to xi. That's why you just have xi instead of xi squared. And then you sum up these cross terms. And okay, here we're summing up some cross terms. Okay, so each of the first one contributes mu, right? And then over here, you have like I squared possible combinations, and each one is contributing a mu squared plus this kind of thing going over all possible lengths. And the lengths are going to be between like 1 and square root t. Yeah, so that's going to be at most the total number of indices. Is that obvious? Uh,
Sure.
okay, this is not so bad. So if you fix I, right, and you increase j, you get a geometrically decreasing sequence. So for each I, you just 1, and then there's size of I ones. Okay, because 1 minus I, gamma to the 1 plus 1 minus gamma squared plus 1 minus gamma q, 1 minus gamma fourth. That's all going to add up to a constant, and there's only size of I starting points. Okay, good. We're surviving. And we put all that together, and you get something like mu times the number of indices plus mu squared times the number of indices squared. Remember, mu is at most 1 over t, because otherwise we're basically done. So mu is very small, and size of I squared is at most t, because there's square root t inside. Okay, uh, so you start getting something like big O square root t of mu. So the second term is going to get killed off because mu is 1 over t, and this thing is at most t. And then I has square root t terms. Okay, good. We're going to do it. All right, so now we're going to just put everything together. I kind of made this slides in a funny way. So initially it's just redoing that simple proof from before. Okay, we already did that. Okay, now when we put everything together, okay, did I get it the right direction? I think so. This should be at least big omega square root t mu. Yeah, okay, so this, maybe I should do this a little bit slowly. This is going to be square root t times mu squared, right? Because each of those contributes mu. Okay, so we're going to get mu squared t in the numerator, mu square root t in the denominator. That's how you get square root t times mu. Okay, yeah, it's kind of crazy. That's okay. Okay, so that is how we show the probability x greater than 0. We got that analysis down, and so that's ultimately what it is. So mu is this guy here, unsat g, and here's our square root t. Yeah. Oh, because that's how we originally set. I was all the indices within square root t of t over 2. And that was very nice because all of those indices have basically the same distribution of kind of random steps. There's not much difference between any of the indices in I. So some level, like, because we want to amplify by a full square root t, basically, right? So it's helpful to get a lot of kind of redundance. Yeah. And once you get past square root t, now the indices start looking so different that the other parts of the argument start to fail. Okay, so up to square root t, you get this kind of nice thing, but you also get this. You want I to be big because ultimately that's how much you get to ramp things up. But beyond square root t, things start to look janky. Within square root t, you can. Okay, good. All right. So that's the powering. Okay, so I left out this one mixing lemma, but you guys have basically done that before. Usually, if I had done this like a week, if we didn't have Thanksgiving, you would have done it for homework. And then also this calculation about you know, within square root t being basically the same. That's just like a straightforward look at the binomial distribution and do some approximation. That also would have been a homework. So they're all doable. They take a little time, but they're not too mysterious beyond what you already have done. All right. So now let's talk about alphabet reduction. Okay, so where are we? We made the graph an expander so that the powering doesn't blow up the size too fast. Okay, but the powering trick required us to, you know, do this kind of super labeling, where each vertex label its whole neighborhood, so we can kind of capture these many step constraints. So the alphabet has blown up. Okay, and now you want to somehow take the alphabet and break it back down to something small. Okay. Uh, Again, it's going to be some crazy stuff, but it's still maybe fun to try to take a moment to try to guess. How can you try to reduce the alphabet size of a constraint satisfaction problem?
You do like kind of dimensionality reduction.
Can you do dimensionality reduction? That's exactly the kind of out of right field connection we want to make. The only thing is it's not clear how our alphabet represents vectors or something. You know, there you're going vectors to vectors, and that feels like a very continuous thing, right? Because you're assigning kind of real values and stuff like this. Um, Whereas this is a very discrete thing. You know, I want to take in discrete letters, output discrete letters. Yeah. Oh, okay, something like compression. What was the closest thing we did to compression? Well, I can maybe Johnson Strauss is one. Yeah. Does any other kind of word association come up? No, it's not a hash function. Uh, I don't know if this is guessable.
For the lectures.
Okay, so any we're going to use error correction. Who's that? Okay. All right. So sure, says Corbett. Um, okay. So our goal is to decrease the alphabet size to a constant. Okay, as you can tell from the pictures, it's going to be crazy. But the first step, okay, is to just take the alphabet and turn it into bits. So I'm going to think of each letter as a code word. Okay. So I'm going to use an error correcting code to reduce to the 0, 1 alphabet, but then every bit will become a vertex. Okay. So I'm going to, so for a moment, we're going to have kind of like hyper edges. So what does that mean? I'm going to take every vertex, I'm going to split it into a bunch of vertices, each of which represent 1 bit of kind of an encoded message. Okay. And otherwise, you know, I have some kind of actually, we'll have some slides in a moment going in more detail, but I can sort of define, you know, try to define a new constraint that takes as input, you know, a whole bunch of bits from the two vertices, you know, tries to decode it and see if it satisfies the original thing. Okay. But what that does, the problem is that this creates like a hyperedge where now like one constraint is over all the bits of either vertex, but it does get the alphabet down to 2 because everything's encoded as a 0 or 1. And then we're going to take each hyperedge and magically replace it with a graph CSP. Okay, so this hyperedge is going to be some Boolean function that takes a bunch of bits and outputs true or false. And we're going to somehow turn that into a bunch of individual edges that sort of preserves some correctness and is robust. Yeah, those are high. Okay, but those are the two high level steps, and then I'll try to go into a little more detail. Okay, if anything, you could walk away just be like, wow, somehow error correcting codes appeared, and that's already kind of cool. At least that was kind of my first impression. Okay, so let me talk about the error correcting code part. Okay, so we're going to come up with, you know, like any code that takes your alphabet and gives it L bit strings for some constant L. A is constant, so L will be constant. Okay, with relative distance rho. So what does that mean? That means that any two code words, well, you know, say rho is like 25% or something. Any two code words where they get encoded should differ in at least 25% of their bits. Okay, so the code, you're gonna take all your letters, embed them into, 20 bits or something, and you want any of the two code words to be pretty far apart. Okay, so you want to load geometry. So a random one is going to probably do okay. Okay. All right. So that's one thing. Now we have to define, the actual CSP. So I'm going to split up every vertex into L vertices, one that represents each bit. I don't know why. I see. And now we're going to have to create, the constraint just used to be defined over two vertices. Now I need to somehow create much bigger constraints that take into account all the bits. So, okay, so I've taken every vertex and blown it up into L vertices, each of which represents one bit. Okay, and now I'm going to define a formula that takes all the bits, for every original edge between two vertices. I'll make a new constraint, okay, that takes in all the underlying bits. So the 20 bits from vertex U, the 20 bits from vertex V, okay? And what it's going to do is because it's going to take some assignment to these bits and some assignments to these bits, right? They might not be exactly the code words, but it's a coding thing. So it's going to, oh, no, it's different. Okay. If the bits for, if the bits for U are exactly the code word for some particular letter A, and if the bits for V are exactly the code word for some letter A2, and if the A1 and A2 satisfy the constraint, then I'll say that all those bits satisfy this new formula. Okay, so in other words, to get that new formula right, you have to get the code words exactly correct, and the words they correspond, the letters they correspond to, need to actually satisfy the original constraint. Okay, so yeah, so instead of using a decoder that finds the nearest neighbor, it's really saying you have to get them exactly right, which at some levels makes sense because we're doing a reduction. We can be strict, right? Because at some level we don't want the bad guys to break the rules. So let's just set some tight rules. So it kind of has to be faithful to this coding scheme. Okay, but we'll see where this row thing becomes useful in a moment. Okay, so the code is going to take your high alphabet size graph CSP and turn it into a 2 alphabet. It's just bits now, 0 or 1, except now each constraint has tons of variables, 20 variables or something, right? Or 40 if it's 20 bits for each vertex. So the next thing we want to do is kind of take these hyper edges and somehow turn them into a graph so that we can get back into the expander logic and things like this. Okay. All right, good. So the next step, which will be even more high level, I guess you got all the details before. This will be very high level, is to somehow replace every constraint, that has many bits going in, with a graph CSP. Okay, and it's going to have certain, robustness properties. Okay, but right now you can just think of each constraint as now being this Boolean function over a bunch of variables. Okay. All right, so here's what the end thing is, and then I'll go through it slowly. So you're going to start off on the left, right, where you have all these kind of clouds of bits, and then you have formulas defined over two clouds at a time. And you're going to make now for every edge that's between two clouds of bits, okay, we're going to make a graph CSP that, okay, so that graph it'll kind of extend the vertex set. So you have your original bits here and your original bits there, and there'll be more vertices in between. Okay. And uh, yeah, this is a little bit abusive, but because everything is a constant at play, you only have a constant number of bits going in, these things will still be constants. That'll be some function of L. It could be 2 to the 2 to the 2 to the L, that'll still be constant. Okay, because L is constant. Okay, and all right. Now, okay, it's gonna have some completeness property. So if you have some bits that make this Boolean function happy, which means that it's exactly the code words of letters that satisfy the original constraint, then you should be able to kind of take those labels and extend them to label everything else inside the graph and satisfy all the edges in this graph you make. So if you're getting the Boolean formula right, you should be able to get the entire graph we make correct. That makes sense, right? Because we're trying to replace this kind of mysterious Boolean function with a graph CSP, and if you're right, you should be allowed to be right. And in the opposite direction, if you have two bit strings that don't satisfy the formula, so it's a wrong answer, okay, then you should not be able to get the graph CSP correct. But even more strongly, you should get a number of mistakes that's sort of proportional to the Hamming distance between the bits you put in and the closest set of bits that would actually be the right answer. So if you have many bits wrong from the answer, then you should get many mistakes in this graph CSP we create. Okay. So that's an important thing, is that we're not just worried about like getting one mistake. We want to get a lot of mistakes if a lot of bits are wrong. Okay. That's going to particularly matter because of this relative distance of the code words that are kind of far apart and stuff. Okay. Okay, so how do you construct this thing? Okay, this is like a crazy thing. It's saying you should take any Boolean formula and basically turn it into a graph CSP. All right. So here you need something that normally would take like a week to prove. So I won't prove. But you can think of this as some kind of like weak PCP with like crazy extreme bounds, but also very strong in a different way. It's going to be weak in the sense that it's not going to be like compact, but it's going to have strong properties. So let me explain. Okay, so I'm claiming that for any language L, there's some randomized algorithm that's sort of like a verifier, takes as input X and Y, and is trying to figure out if X is in the language based on the proof Y. Okay, but here's the first catch. Anyone want to try to guess how long the proof will be? No. The proof Y. The proof Y. And the 5 minutes never stopped me before. Okay. So normally with like MP problems, you want the proof to be polynomial in size, right? All right. This one is going to be doubly exponential. Okay, it's going to be a massive proof. Okay, so there exists some massive proof. Okay, and the algorithm is randomized. It's only going to look at 3 bits. Okay, so it's not efficient. It's only going to look at 3 bits. If X is in the language, it should always accept. Right, so you have some soundness. And then for completeness, if X is not in the language, no matter what the Y you give, you should reject with some error proportion to your distance from anything in the language. So if X is very far from anything that should be accepted, you should be rejecting quite often. So if half the bits are wrong, you should be rejecting half the time. Okay, times 0.001, proportional to half the time. Okay, could be any constant. This is called a universal tester. It's an extension of something called a dictator test from Boolean analysis. Okay, which involves Fourier analysis and things like this. Okay, when I've taught this before, because of the whole week you don't draw any graphs or any pictures, it can be a little abstract, and so I've decided not to. Okay, all right, but this is sort of like a PCP, but with crazy bounds, right? The proof is super big, but you reject with some probability, things like this. Okay? This is holding for any language, though. It's not assuming that it's an NP and has a polynomial time verifier or something like this. So any subset of bits, you can come up with this tester. That's why it's called a universal tester. Okay. All right. So now we want to somehow take this universal tester, turn it into a graph CSP, and here you might be able to guess a little bit. All right. So you have this randomized algorithm. It's going to query 3 bits, and otherwise it's kind of doing something that pattern matches, right? Like it always accepts if X is in, and it's going to reject with some probability proportional to how bad X is. Okay, which is kind of what we're looking for before. We wanted to make sure that your unsat for the CSP that we make is kind of proportional to how far your inputs are from a correct answer. Okay. Now you want to try to take this universal tester and turn it into a graph CSP. Any ideas? So you need to make edges. You make constraints. Do you remember what we did before when we took PCP and turned it into constraints? So a natural thing is to try to convert all the random bits and make a constraint for each one. There's one catch though, which is that our tester makes 3 queries, right? And edges are usually between 2 points. Okay, so we just need to come up with some kind of trick to get around this. So, okay, so you have your kind of Boolean function f of x and yeah, or alxy, right? So we're gonna first make a vertices representing all the bits at play. So all the input bits x1 through xn and all the proof bits y1 through yp, where p is 2 to the n. Okay, and they're going to be given an alphabet of 0, 1. Okay, and then for every coin toss, uh, I'm going to make another vertex. So we know this algorithm is a finite number of coin tosses. It could be a gazillion, but it's finite. For every outcome, I'm going to make a vertex. Okay. All right. So, and now one thing I'm going to do is that the alphabet for these is actually going to be a 3 bits. All right. Does anyone see now? Okay. So here's what we're going to do. So the 3 bits are going to represent sort of the outcome of doing 3 queries. Okay, because we know the tester makes 3 bits. So let's say that when you toss coins and you get some outcome omega, right, these are supposed to be omegas. Okay, it says that you should query, I don't know, xi, xj, and yk. That just for example, it could have been xi, yj, yk. It could have been yi, yj, yk. Okay, so now we're going to make 2 kinds of constraints. Okay, so let's say that I have some vertex labels pi, so it's assigning alphabet to these variables. So I want to do 2 kinds of things. So the first kind of constraint is just like a self loop at oh, how do I do this? Okay, I'm going to make a self loop as z omega. So if z omega, this represents some like bits of you queried and you got 0, 0, 1. If al would have accepted on this, that will be my constraint. Okay. And then the other is you have to make it consistent with the actual xi, xj, and yk and stuff, right? So we're going to add 3 constraints saying, okay, your first bit as z omega has to agree with xi. Your second bit as z omega has to agree with xj, and your third bit has to agree with yk. So that's our trick, right? So basically the problem is that these testers query 3 bits and edges are between 2. So I make a one vertex that represents the whole outcome of all 3 bits. And then I just add edges to make sure they agree with the actual bits. Because I can't draw a hyperedge between these 3 vertices. That's all. Yeah.
Query the input bits instead of just the proof.
Why would it? Well, I mean, at some level, you're asking yourself, does y prove that x is in the language, right? So you probably want to be aware of x.
Okay.
So this one, we're also counting how many times it looks at x. Whereas in MP, you're allowed to look at x, and then you query parts of the proof. Okay.
What is 3 bits?
Yeah, because yes, yeah, it only needs to use 3 bits. Yes, we could do it. It's written up. You can read the next chapter in the book. You're not in the class anyway, so you can. Yeah, plenty of time. Okay. All right. Okay, so that's the idea of creating the universal tester, which is a bit of a black box, of course, but you can think of it as some kind of bizarro PCP looking thing and turning it into a graph CSP. All right. So is there much to do here? Okay, so all that's left is kind of proving this thing works and preserves certain unsat things. Okay, so let's say G is what you started with. G bar is after you do this coding and universal tester and blowing everything up. I first want to show that unsat doesn't go up. Okay, and that's kind of simple. If I have some labeling to the original graph, okay, then I'll just label the bits based on the code word, right? So whatever label I gave here to this vertex, I'll just use those bits of the code word. And something like this, okay? And you know that if you got this, if the original labels for U and V got this constraint correct, there's some way to label everything inside to get everything correct. Okay, so you just extend the labels for all the correct things. Okay, now everything you got correct in the original formula, you're going to get correct in the blown up formula. And it's important to point out that all these graphs are the exact same size because we maintain regularity all throughout and things like this. Okay, so if you get like 10 graphs correct, that's still, or if you're getting 10% of the graphs correct, you're getting 10% of all the constraints correct because all the graphs are the same size. Okay, the other direction. Okay, this is maybe the more interesting part, but I'll go through it somewhat quickly. Okay, so okay, now you want to show that unsat in the new one is at least something proportional to rho times the unsat of in the original graph. Okay, and then once you get both back and forth, then the unsat's roughly preserved. Okay. Okay, so let's say that I have some labeling to all the bits in this blown up problem. Okay, and the natural way to recover assignments in the original graph with the original letters is to just decode all the bits with your decoder. Okay, now for a particular edge, if your assignment fails that edge, I claims okay. If you assume this is true, okay, so it's saying that if when I extract the letters, I get an edge wrong, I'm going to get at least a row fraction of the graph wrong. And if that's true, that this part's not so difficult. You know, you're just averaging over all the graphs, and every graph you get wrong, you're getting row fraction of the edges wrong. Okay. The real interesting thing is how come if the decoded labels fail the constraint, how come you're getting a row fraction of that crazy graph CSP wrong? And this is where that relative distance, the code words being far apart, becomes helpful. Okay. So let's look at an edge that you get wrong, right? If you got it wrong, then you know that those bits have to be pretty far from any pair of code words that's correct. Okay, so have some relative distance proportional to rho. I guess it's rho or 4, I forget why. Okay, but something proportional to rho, because if you get things wrong, you have to be far away. And that means that because GE is robust, right? If you're getting many bits wrong, then that graph you create, you're going to get many edges wrong, no matter how you extend the labeling. And that's it, right? So if you decode and you get wrong letters that don't satisfy the constraint, you know that because the coding places code words far apart, that the bit strings are very far from anything that would have been correct. And in that kind of robust graph CSP guarantees that if you have many bits, you're many bits far away from a right answer, you have to get many edges wrong. Okay, so I think that's it. That puts everything together. That's all the 3 steps. You know, if you want to fill out this table, the expander makes a constant degree, the powering blows it up, and alphabet reduction does something mysterious you don't care because you're going to fix it next time. For the spectral gap, you know, you get it up to a constant just by overlaying an expander. It gets worse, whatever. The alphabet reduction messes it up, you don't care. The unsat is maybe the interesting part. It goes down by a constant in the expanderification step, and then you get to ramp it up by roughly a square root t factor times some constant, and then you lose another constant in that last step. But these B1, B2, B3s are independent of t, so you just have to make t big enough so that you make some progress. Okay, and then the alphabet size, powering blows it up, and then this crazy graph CSP brings it back down. Okay, so somehow this works. Okay, in fact, these parts were kind of clear because you get to completely reset with some of these strong operations. And the real thing is just getting some square root t times something, and now you can just make t a big enough constant that you make progress. Okay, that's sort of the high level proof. It's not all the way to 1/2 and things like this, but at least you'll see a lot of the ingredients that goes into something that's otherwise kind of very profound and very consequential. Okay, that's it. Any questions? You guys can take off. Sorry? Well, you can't do better than 7/8 on 3 sat. But in general, there's limitations to approximations, all these things.